Hi guys, welcome back to my channel. Let's talk about mirrors and lens today. So we're going to first dive into the concave and convex mirrors, and then a concave and convex lens, and then the power of lens, magnification, some biological application, and then finally the scene length equation. All right, let's dive into this. So as you can see here, first I drew two different mirrors, okay? The one on the left is the concave mirror, and then the other one is the convex mirror on the right. And then the concave mirror is really the one that is convergent, okay? What does that mean? As you can see here, this concave mirror is really bending the light toward a single point, and then that point is this focal point, right? This focal point. So if you see the picture, the purple line here, it hits the mirror and then it reflects, right? It would pass the focal point, and then so does the green line. Then it hits the mirror and it reflects. They both bend the light toward it's a single focal point. All right. So that's why this is a convergent lens, a convergent mirror. Okay. And then the other convex mirror is really divergent. As you can see that they do also, the incoming light is here, right? And then they do also converge at the focal point, but then they later get dispersed or diverged, if you will, right, to the other direction, so that we call them divergent mirrors. Okay, all right. So the other difference between a concave mirror and a convex mirror is that their focal length, one is on this side of the refraction side of the mirror, right? And then the other focal length of the convex mirror is really a negative one, because it's the opposite side, right? As if the mirror never ever reflected the light, right? So that just not intuitive. So we say that focal length is positive, whereas this positive focal length is really like more intuitive, since we know that the mirror reflects light, right? So all the light, everything should go back somewhere, the same direction, the same side as the object, right? Okay, so that's why one is a positive focal length, and then the other one is a negative focal length. Okay, all right. And then we also see that, as you can see the image, how the image is formed. So this image here versus this image here, we see that the concave case, we have this inverted upside down image, right? But it's a real image, okay? Whereas the convex mirror really gives us this upright image. It is just what it is, right? But it's not a real image. It's a virtual image, okay? All right, so that's it. This is more really like when you see yourself in the mirror, right? You see yourself on the other side, and then you're upright, but you're virtual. If your friend was touching the image, then they could really feel you, right? Because it's virtual image. All right, so that's the mirror, right? It's pretty straightforward. Okay, I think all the yellow highlighted things are what we need to just memorize, okay, on MCAT, because really on MCAT you don't have the time to process all this and draw all these ray diagrams, so we really want to commit it to memorization. Okay, all right, now let's switch our gear to lens. Okay, and lens is more yield than mirror on MCAT. Okay, so as you can see, I also draw two types of lens here, right? One is the concave lens and one is the convex. Okay, so the concave is always the one that's, it's kind of a bending inward, and then the convex one is the one that's bending outward, right? But the difference is that now this time the concave one is not the divergent one as the mirror, right? It is not a convergent one as the mirror, but a divergent one for the lens, okay? And then the convex one is not divergent as the mirror, but in this case for the lens, it's convergent. Okay, just flip it, okay? All right, so we know that the mirror would reflect, right? But what is the lens? The lens, intuitively, we think it would refract, right? Reflect of the mirror versus refract, right? Means that the light can go through the lens, right? Assume that it's transparent, okay? So yeah, so that's what the lens do. So we would think it would make sense if the light can pass through the lens, right? If the focal length is on the other side, then we would think, oh, it has a positive focal length, right? Positive focal length. That's the case of the convex lens, right? Whereas the concave lens, it really have a negative focal length. It has a negative focal length because really it really just converges at this same side of the object, which is not what refraction is, right? It's what reflection is, right? But and then it diverges, right? So that's why it's a diverging length, but also it has a negative focal length. Okay, all right. And then as you can see the image, that the negative focal length, the concave one, has this upright virtual image, right? When the image is upright, it is always virtual, right? When it's a real image, and most likely it's a upside down inverted one. Okay, all right. So that is the concave lens and convex lens. Okay, so the convex lens actually gets complicated. Okay, there are different scenarios that either we have this virtual upright image or real invented image. Okay, it depends. Okay, so in the first case of this picture that you see, okay, we have three cases, 1, 2, 3. Okay, so the first case is really, you can see the DO, the distance of the object, is smaller than the focal length, right? What do I mean? You see the object is really here, right? If I use this, the object is really here, but the focal length is on the left side of it. So really the distance of the object to the lens, this distance, is really smaller than this distance, right? So in this case, what kind of image do we form? In this case, we form this upright virtual image, right? Okay, and then the second case is really the distance of the image is larger than the length of the focal length, right? As you can see that this B, you can just imagine this is a O, okay, the object. See, the object have such length, and then the focal length have such length, so that the length of the object is larger than the focal length, right? So that in this case, the image we form is the inverted real one. Okay, all right. So what about the third case? The third case, we see the object and the focal length, they're at the same point. So really DO equals F in this case, right? So in this case, they can never converge. Okay, so you basically get, it's a parallel. They're always parallel, so there will be no image. Okay, all right. So that's the three cases for the convex, okay, for the convex lens. All right, so before we dive into the biological applications, I also want to mention that we want to know, sometimes MCAT wants you to calculate the power of the lens, right? So the power of the lens is basically 1 over, this is focal length, okay? So as long as you know what's the focal length, and usually focal length can be calculated through the sine length equation, right? Or can be told by the question, right? So that's how you calculate the power of the lens. And then what is magnification? So magnification is basically like a magnifying glass, right? How the extent that this magnifying lens that magnifies things, right? Okay, so in this case, then we know that the magnification, we say little m, okay, it's negative I over O. Okay, I is what is the image distance, right? O is the object distance, right? Or it is another equation is the height of the image over the height of the object. Okay, so that we see that there's this negative sign here, right? So the O, the distance of the object, it's always positive. It's always positive. Okay, this I can be positive or negative. Okay, so when you plug in either positive or negative, then you can get either the M is positive or the M is negative, right? So when the M is positive, the image is really upright. And then when it's negative, the image is inverted, okay? And then the magnitude of the M, if it's larger than 1, then it's magnified, okay? And then, but if it's less 1, then this is not a magnifying lens. Because the image is reduced, okay? And then now let's talk about when this distance of image will be negative, okay? So that we know that all the image and focal points on the opposite side of the lens or mirror as the eyes, as the observer, are negative, okay? What do I mean here? So, for example, in this case, this eye is is negative, right? So if I say, okay, this image, I mean, this is like a 1 meter, and then you would know, you plug in the I equals -1, right? Why? Because it's really on the opposite side of your eye, right? In this case, your eye, let me draw a eye. right? Your eye is really on this side, right? You're looking at the mirror, right? And then you see the image in the back, in the other side of the mirror, right? So your eye is here, and then this image is really formed on the opposite side as your eyes, right? So in this case, we say this is a negative, okay? Okay, and then in this case, you see the image is formed on the same side of your eye, right? Your eye is here, so that this eye is really a positive, right? Okay, like what about this case, the concave lens? The concave lens that, okay, the eye is actually here, right? As I draw here, the eye is here. So the eye is here, then your image is formed, in this case, is on the opposite side of your eye, right? So the eye is negative, okay? Whereas your eyes are here, right? Your eyes, and then the image is formed on the same side. So in this case, this eye is positive, okay? So you just plug in the eye, right? And then over the always positive, the object distance, you can get either positive m or negative m, and then that denoting the different status of the image, right? And then also you may say, okay, but what about this hi over ho? Will they both always be positive? No, not necessarily. If the image is formed upside down, then the height is a negative, right? So you can still get either positive m or negative m, okay? All right, so that's about the power and magnification, okay? Okay, now I think we can move on to the biological application, okay? So the biological application is that human eye lens, okay? So the thing I highlighted here, human eye lens are always what? Are always this case. This convex, okay? This convex convergent lens, okay? Let's write it down. Convex, convergent, okay, 2C, okay? See, that's the human lens. It's convex and convergent, okay? So these are the normal situations when, these are not the normal situations. These are the cases when you have when you're nearsighted, right? Myopia, or farsighted, the hyperopia. So the correct way is really to the normal eye without these conditions. You want this to converge on your retina, right? This is the retina. This is the retina. So this is the goal. But as you can see, the hyperopia, it converges here, right? Behind where the retina is, okay? Behind where the retina is. So in this case, we need a convex, right? We need a convex lens. So this is a convex to kind of correct it, so that after you put another extra convex lens on top of your lens, then the light, the incidental rays can converge at this right spot on the retina, okay? And then the myopia, the nearsighted, is that the lights, they converge too soon, right? It hasn't got to the retina yet. So you use a concave lens, okay? This is a concave. You use a concave lens, that's your eye contacts or your glass, right? So to correct it so that the light can converge at the right spot, okay, which is the retina. Okay, perfect. So that's it. And then the other biological application is really this muscle called a ciliary muscle. Okay, it's right about here. Okay, right about here. And then this is just a ligament. Okay, and then this is your lens. Okay, when you have when the ciliary muscle, when it relaxes, so this is the case of relax, you can see stuff from far side, okay? In this case, when this muscle relaxes, your focal length increases, okay, and then this means what? The power of the lens would decrease, because they're inverse relationship, as we discussed here, right? Okay, and then the other case is when you flex the muscle, or you say contract the muscle. Okay, when you contract this muscle, then your focal length would decrease, your power would increase. And then in this case, you are seeing the things, when you are seeing things that's close by, you would flex, you would contract this ciliary muscle, okay? All right, and then as we age, so age is proportional to the focal length. As we age, we will have a longer focal length, right? We'll have a longer focal length. So this makes us to be able to really see far point, right? It will make us hard to see that's close by. So that's why elder citizens, they wear the glasses for them to see the close by stuff, okay? All right, so that's the biological applications. And then lastly, we want to talk about the single length equation, right? The single length equation is really just 1 over this f is the focal length, okay, either positive or negative, and then equals 1 over the distance of the object, which is always positive, right? So this can be positive or negative. This is always a positive. And then this I, the distance of the image, can also be positive or negative, okay? So yeah, that's how you plug in the number. But it doesn't get that easy, like MCAT doesn't really give you such a straightforward way to solve it, right? It really gets tricky. That, for example, we have an example here that tells you the focal length is 2 meters, okay? Focal, whatever scenario it applies, okay? And then the object distance is 4 meters. Then the question doesn't ask you, okay, what about the distance of the image? Then it will be easy. You just plug in, right? You just plug in 1 over 2 equals 1 over 4 plus 1 over I, right? And then you can solve the I, and then you will get your answer. But it doesn't ask you that. It asks you what is the ratio of HO over HI, and is the image upright or inverted, right? So this is getting tricky. So we have to have this background knowledge that this HO over HI really equals to DO over DI, okay? So really, you still need to solve this DI, right? And then you can know the ratio of DO over DI. Then you know the ratio of HO over HI, okay? So yeah, let's solve it, okay? All right, so let's do it. So it's 1/2 minus 1/4 equals 1I, right? So this is 2/4 equals 1 over I. So that gives me, so I equals 4, right? 4 meters. Okay, so that I know that DO over DI, what is DO? DO is 4, right? What about DI? DI is a 4 meters as well. We just calculate. So that gives me the ratio of 1. And then that equals to HO over HI. Okay, that will be the answer. And then is the image upright or inverted? And we see that this HO over HI is 1. But we know the magnitude really has this equals to HI over HO, right? Remember here? Right? So if HO over HI is 1, then HI over HO is also 1, right? It's also 1. And then we say that when it's positive, then it's upright, okay? So in this case, the image will be upright, okay? So this is how single length equation is tested on MCAT. It's really more nuanced and tricky than you have imagined. Okay, I hope that's helpful.